So what is the rare Earth hypothesis? The rare Earth hypothesis, it's basically as it says. It's a hypothesis that says that Earth actually is super rare. That's not like a common thing that we have a planet like Earth, and that the chances for us to exist are so improbable that that we're kind of unique in a way, right? Like, if not unique, like very, very rare. That's why it's like this. So it basically says that the existence of life as we know it, right? We always have to say as we know it, because we don't know if there's other life out there that lives under completely different conditions than we do, yeah? I don't know, maybe a species can live in a gas giant. Who knows, right? Who knows? Maybe there's a species out there that doesn't need oxygen to live. Who knows? Who knows? Or CO2, or all of that, yeah? So existence of life needs... Okay, that's bad. Write this again. An improbable interplay of events and in an astrophysical and geological sense, of course, yeah, circumstances that astrophysical and geological, goddammit, geological. And we learned basically over the course of the last streams why that could be, why this actually is a possibility, that this is the case, right? I think first thing we're gonna go is in the rocky planet, because if we talk about life as we know it, we talk about a planet that is rocky, right? So why do we need a rocky planet? So the structure of Earth needs materials, right? It needs iron, magnesium, like some metals, right? Good evening, Boric. Hello. Magnesium, silicate, right? We talked about silicate, and that is only for the structure, right? Now, if you go about the heat, like we have heat inside Earth, right? That we need to, like for tectonics or like the heat up the Earth in general, right? We need other materials. What do we need for that? For that we need like uranium or thorium. And now for life. Now this is just to form a rocky planet, right? But we also want life on that planet. So the structure of life needs make it blue. No, you don't need uranium for the rocky planet, but you need it for the heat inside, right? Like we have heat, like our Earth inside is a heated core, and it causes plate tectonics, for example, that we need to form land masses, for example. It's very important actually, or for the carbon cycle, right? The carbon cycle of Earth needs that too. Don't trust a sheaf-laced strike. Yeah, exactly. It's heated because of radiation. Yeah, you have radiation in the core, and that heats us. Yeah. What was I saying? Oh yeah, okay. So for the structure of life, carbon. Yeah, exactly. Exactly, Roxanne. We need carbon. We learned that. I like, I don't know, nitrogen, oxygen, hydrogen. I mean, the universe has massive hydrogen. We don't have to worry about that actually. So let's just make it like point. Actually, it's everything here. Like it's probably more. I don't really know. And so that's for what we need, like not just rocky planet, but for a rocky planet that is in an Earth condition, right? That has the condition of Earth. Now remember back to the second science stream. What did we learn in the second stream? We learned about habitable zones, and we learned one important thing in there. In the end, we learned about the galactic habitable zone. Now, people who haven't watched this, we're gonna go and have a little recap, a very little one, about the galactic habitable zone, and why this is like one argument for the rare hypothesis, Earth hypothesis, right? So, remember, the galactic habitable zone. Gravity? No, it's rocky. Like it's just rocky, but yeah, there is not much gravity can do other than break it down, I guess. Netted by gravity? No, it's the radiation actually that heats us. Galactic habitable zone. What does this mean? We have a galaxy, and not every part on that galaxy is actually habitable, right? There are a lot of parts in the galaxy that it's very unfavorable conditions for life. Now first though, let's go back to the rocky planets that we need. So there are regions that in galaxies that do not have enough metal actually to produce rocky planets, right? So let's say here, not enough metals. For rocky planets, right? So let's say this. So what does not have enough metal for rocky planets? Small galaxies. Elliptical galaxies. And this is not to say that it's impossible that they have rocky planets, just far less, alright? Far less. So there is like a far less chance for rocky planets to form, yeah? The edge of the galaxy. The edge of the galaxy. A globular cluster, for example. Or the early universe. The early universe, right? We know that metals are introduced into the system due to supernovas. Like the early universe didn't have enough metals to produce rocky planets because it needed a certain amount of supernovas to produce them, right? So, why is universe? Why is this important? Well, we come back to this later because time is an important factor for all of this as well. And so what we said, it has another condition though, the early universe, and that it has the same time they have not enough supernovas happen. They also had a lot of supernovas events that were happening. So you have to see it like this, like an evolution, right? Not enough supernova events happened in the early universe to form enough metal, to form enough rocky planets, but a lot of supernovas happened to form the rocky planets later on, right? With the next generation. So, too much supernova event. That also happened in the early universe. It's not really a contradiction, right? We're talking about the next generation. So what is the problem here? Too much radiation. Which kills life, right? Too much radiation kills life. As we know it, maybe there is a species out there that thrives on radiation. Who knows? Who knows, guys? At the same time, if you don't have enough events, you don't have enough metals for the rocky planets, right? So that's the weird thing about it. Don't have too much, but you need some. I have too many questions. It's really interesting. If you have a question, ask. Yeah. Are those there are only water planets? Most likely there are only water planets. Yeah. And if you don't have tectonics, then landmass will never go over the water. Water planets actually have a very long biosphere, so they can survive quite a bit, the biosphere in that. I have it on my YouTube channel, guys. I have a YouTube channel. You can see it in the description of my channel, and I saved them there. But I also saved them on Twitch. You can watch them off, but people prefer to watch it on YouTube, so I put it on YouTube. I don't do anything with them. I don't cut them. I just put them here because people ask me to, right? Because some people don't like to use Twitch for the VODs. But yeah, I saved them on Twitch as well. Thoughts on colliding galaxies? We will collide with Andromeda. Everyone knows this, and it will do nothing. Yeah, the collision parameter for stars is it's so large. Nothing will happen. Okay. Then. Another thing, do we? I shouldn't have made it that big. Let's see if we can make the rest to here. Okay, another thing we have to see is the galactic center. Like we talked about the edge of the galaxy not having enough metal, right? But there's also the galactic center. And in the galactic center, the gravitational disturbances, like it's really unstable. The galactic center is it's a clusterfuck. Yeah. I lost part 1, guys. I forgot part 1. I forgot to save it. It was my first one. I didn't think about that, and I think about making a YouTube video for part 1, just not a stream, just a video to round it up, right? The part 1 was about how we find exoplanets, which I think is a really cool topic. I will see about this. I will either make it just a video to conclude it, or I will maybe make a stream with the same topic again. I don't know. I think about it. The purpose of this, because I love science, I love astrophysics, I want to share knowledge, and I want to gain knowledge, right? If I have to prepare these, I have to study myself. I study physics. I have a bachelor degree in physics. I'm doing my master's currently, and this helps me to study for topics I either don't know much about myself, or just in general share it with you because it's super cool. Yeah, I want to spread the knowledge, and mostly fun. Yeah. It's so much fun. I'm enjoying these too much. So I'm enjoying these very much. Like I think it's super cool. Also, like yeah, I don't know. Like I don't say that I know everything here, and that I'm like the authority on the knowledge on this subject, because physics is a broad subject. It's very hard to learn. Sometimes you forget something. And it keeps me up to date, right? It keeps me up to date, so... And you may always ask questions. Okay, the galactic center is gravitational unstable. For like... Why is it important? Because let's say a rocky planet forms in a habitable zone of a star in a galactic center, but because of gravitational clusterfucks, it doesn't actually. It's not in orbit for that long, right? And then there is no time for civilization to evolve actually. And also on like energetic levels, it's super violent, right? Violent on energetic levels. Okay. Then we have. I have to grab some food. If you're finished before I get back, then I will catch you again sometime. Alright, Glitch! You enjoy your food. Yeah, I know I have it not at the time I planned to do it today, so. Not your fault. No need to colonize planets unless it has oil. No, we're gonna go away from oil, okay? We don't need oil anymore. Okay, so then we have in the galaxy an area of where we have only very young stars, right? So inside the galaxy we have areas with 2 young stars. Why does it matter? Because then there's not enough time for life to have developed yet, right? Not enough time for life to have developed. And then there are areas with 2 old stars. Areas with 2 old stars. And that's the other way, not enough time to survive, right? If the star is too old, then it goes supernova, boom, civilization is dead, right? Or if it doesn't go supernova, it's like just doesn't have the power anymore to support the life, right? How much time it needed? That's a good question. That's a good question. We talk about this later. So this is only about a place in the universe, right? This is only about like universe in general and the place. I think I just take a new slide because this is no. So basically, the universe is big. But mostly unfriendly. Host for life. So it's either it's like too hot, too cold, too dark, or like not composed of the right elements, yeah. Okay, now let's say we find such a place though. All right, let's say we find a place in a galaxy. That's really cool. Like we can settle there. It's fine. It has there's enough metals. The star is just right, and we have a rocky planet. Now, what are the conditions for that planet then, if we have it, to like harbor life, right? So system and planet factors, like just now we had the galactic vectors, and now we take like the system and planet vectors, right? So let's make that right. The first one was too hot. The second was too cold. The third was just right. Just like your ex. you don't like, yeah, it's the same like with cooking. Or like if you cook a steak, I don't know. You want it just right. So what is important if you found the place, what then, right? So first thing, distance from the star. And same thing again, you want it just right? Why is that? Well, we want to spend a long time in the habitable zone, yeah? So time spent in the habitable zone is very important. If we are too short, then we don't have enough time to develop. Like pancakes, yeah. Like we want the most amount of time we want spent in the habitable zone, right? But the habitable zone is shifting, as we saw in the stream. It's shifting. It's actually getting narrow, and that's why it's important to be at the right distance of the star, right? What also is important is the mass of the star. Why is the mass of the star important? Not only the UV radiation, but also the lifetime, right? Like very massive stars have only a very short life. Like our sun, for example, has like approximately 9 billion years to live. Right? And our sun is a low mass star. Higher mass stars live way shorter, and if the stars live too short, then the civilization will not have enough time to develop, right? What is also important, the mass of the planet. It's like important for, like, for example, there's like something called super Earth. Super Earth actually have a longer lifespan of the biosphere, because they're like the cooling is slowed down, right? If it has more mass, then lower cooling rate, and then it has longer plate tectonics, so it can support the carbon cycle way longer, right? So lower cooling rate. Or actually higher mass. Lower cooling rate. And if you want to read up on this, you go to like super Earth. Super Earth. They have supermassive planets basically. Unless human finds it, yeah. It's always the factor. It's always the factor, right? Another factor is Jupiter-like planets. Like if you have Jupiter-like planets in the system, how can this affect that? Having Jupiter-like planets affects us in a negative and in a positive way, right? So you want it not too close. Because it disturbs stuff. It's disturbed planet formation, right? The asteroid belt we have in our system is most like, there's this hypothesis that it was caused by a planet that was about to form, but Jupiter disrupted this, yeah? It could also cause unstable orbits. Hey, XP6. Exactly, we have the positive note on this. Not too far. Because it could be like asteroid catcher, right? So it protects us a bit. Like it has a high mass, so like gravity is higher, and like it could catch some asteroids that would otherwise hit us. So yeah, it has a negative and a positive thing to it. Tectonics. We want plate tectonics. What do tectonics do? They magnetic field, like, right? They provide the magnetic field. And they're like the thermostat of Earth. They build landmass and they heat us. Build landmass, heat. Beams with pride. Very good. Our moon, by the way, too, right? Our moon, by the way, too. Magnetic field, we know this. Everyone knows this, right? Magnetic field. We need this to keep atmosphere. So magnetic field deflects cosmic rays. That would otherwise slowly destroy our atmosphere by solar winds, right? Tilt. We need the right tilt. Why do we need the right tilt? Because mostly for like a moderate climate, right? If the planet is tilted too much, then only one side gets heated by the sun and the other side is in the dark, right? Our Earth has a very slight tilt of 22 degrees, I think. So tilt is important for the distribution of radiation. Which causes a moderate climate. The smaller the better, right? Smaller is better. Earth has like 22. I don't know if it's like, I think 22, something like this. Okay, yeah. That is important. Now, what else? The moon. I talked about this. The moon also needs to be at the right distance, right? What the fuck? Moon at the right distance. What does the moon do? It stabilizes us, right? Stabilizes the tilt. Stabilize? Is this how you write it? I hope so. Sorry, my writing is not as good in English. And the tilt and the rotation of Earth, right? The rotation on Earth slows. It slows the Earth rotation, which helps with a moderate climate. I guess. Actually, I don't know. Orbital stability. Orbital stability. Like eccentricity. Eccentricity is important. And yeah, needs stable orbit. I mean, what else is there to say? What else is there to say? If we have a very large eccentricity, that might be bad, because then we will be like too close to the sun or too far away, like too many extremes, right? And if the orbit is too unstable, then we don't have enough time. The right atmospheric properties. The moon is slowing down the Earth's rotation, and it, of course, it's physics. It has to be equalized, right? Momentum, rotational momentum, and because of that, the moon is going away. The moon is leaving us. So yeah, because it slows down Earth, something has to suffer. and the moon is leaving us. Say bye to the moon. It's going away. Right atmospheric properties for like temperature and pressure, composition too, right? I mean, yeah, composition, yeah, atmospheric composition, or like right amount of carbon. Let's say right amount of carbon. We learned in the last science streams when we talked about the Earth system model that carbon is very important for development of life. So we need a minimum to support life. And if we have too much, we get runaways effect, right? Then we cannot stop it anymore. Which might happen to us, who knows? We don't want this. We don't want the runaway effect. We really don't want that. What comes to... Oh, I actually don't know. Good question. I think the moon leaving, probably. I should look that up. It's a good question. Actually, I think... Wait, how many centimeters does the moon leaves us in the year? Only some centimeters? A very small amount. Like 2 maybe? I actually don't know. Okay, like if you want, Google it. How many centimeters the moon is leaving us per year, and then you can calculate it, right? Then you can calculate it. You know, I already told you the sun is like 9 billion years, but yeah, I would say too. If we fuck up Earth anyway, before anything happens, we fuck up Earth. So, the Earth doesn't stop moving. I mean, if the moon doesn't slow us down, we would actually go faster, right? So the first thing we have to do, guys, the first thing we have to do is, like, we just saw that we need to find a habitable place on the galaxy, or in the time of the universe even. So, and then we need a lot of stuff to happen. So what we need to find the habitable. I can't write properly, guys. First we need to find habitable time period. In universe lifespan. So this is the first thing we need, right? Lifespan. Lifespan. Okay, let's say this. After this, we need to find a habitable galaxy, alright? Find habitable galaxy. If we found this, we need to find a habitable spot in this galaxy. Find habitable spot in galaxy. Okay, let's say we found this. Find the system. With planets that fulfill all the conditions we said earlier. You know a good spot in the Milky Way galaxy? Yeah, me too, yeah. Find a system with planet. No, actually with rocky planet. With rocky planet. in the habitable zone that satisfies all the other conditions. Satisfies, that's correct. At least partially, right? Some are more important than others. This is okay. It's all a recap. If you want to read more, I think yeah, we talked about this. Was it like this? Habitable zone was the second science stream, right? Yeah, I think so. So habitable zone is actually saved. Okay, now let's say we found this. We still need life to develop, right? If we all of this, so the next condition would be life needs to develop. Life and this is only life. Now we think, hey Sins, hello, welcome. We think that we might be, I mean, this is still up to debate, right? The Cambrian explosion, we talked about this last time. So Cambrian explosion events. Explosion event, that was the last science stream for biodiversity. So we know that the biodiversity happened, that an event where biodiversity suddenly increases happens. We don't know if there might be another event like this that is invisible to us because we cannot find the fossils, right? Because it's very easier to find fossils with bones in it. But we do find like fossils without bones, I think. So it produces basically a large number of new species, right? And this like increases the odds that an intelligent species is going to develop out of it. Why is aliens always presented as bipedal with two eyes, nostrils, ears and mouth? Wouldn't an alien be completely different from humans? I think if we are developed on Earth, like if we're talking about life as we know it and developing on Earth-like planets, maybe even not. If you have the same conditions, like, I don't know, gravity, atmosphere, then maybe the same stuff wins out, right? We don't really know. It's always a good question. Just learning about things I never understand. Ah, come on, you understand. 3.8 centimeters per year. Nice. So that's actually a lot, right? Like, isn't that a lot? I don't know. I would say it's a lot. Yeah, I mean, it's always the question. We talk about life that we know it. It's very important. I said it in the beginning, when we talk about this, existence of life as we know it. Because other stuff, it's hard to imagine, right? There might be aliens out there that function completely different than us, yeah. And yeah, that's just, we have to keep that in mind. Water is important because of a medium for molecules to interact. Yeah, I mean, water is very important for life as we know it, definitely. And I don't know if there's something that we cannot even imagine anymore. But basically, if you go like on the basics of our life, then yeah. Hey, hello new people. Welcome new people, by the way. But the moon's outer spiral is dwindling as the distance from Earth decreases and its tidal forces get weaker. This alone should be enough to prevent our satellites from ever leaving orbit around Earth. Oh, actually, yes, completely without intervention from some outside forces. Disclaimer, cannot verify the force. Yeah, okay. So they say it's just gonna stay. It's just gonna be very far away than it is now, right? Portrayal in media is easier for audience to relate. Yeah, probably. Yeah, yeah. Title locked. Yeah. Yeah, we look for water. Yeah, we look for water as proof of bioscience. Yeah. Yeah, exactly. We don't know what to look for other kinds of life. Yeah, and water is always a very important factor. As Ainimo said, that is very true. Like, I don't know much about biology. Like everything I talked about basically last stream, I had to really look up myself. I don't know about all the cell stuff, molecular stuff. So I don't actually wanna go that deep in there because like I learned physics, not biology, and it's super interesting though. It's super interesting, yeah. Okay, so as I said, we learned that maybe we need some event like the Cambrian explosion that produces large amount of biodiversity. Maybe it happened before there and we cannot find it because it's invisible to us, because of course it's hard to go backwards, right? It's science. It's up to change, right? Maybe one day we're gonna find something that completely changes our outlook of it. But we do know by now that there was a time where biodiversity exploded, all right? And maybe this is needed for complex life, but we don't really know. But this is all, we talked about it the last Ryan stream, so we don't talk about that too much now. So basically, this is all this is what we have. You can see that there's a large amount of interplay, a large amount of like the right time, the right place. It's just so much that we could maybe conclude that this is really rare. I wonder if we find other flat planets like Earth. Yeah. So, yeah. But maybe simple life. Simple life could be more like common than complex life. So it could be more probable to develop. And yeah, most likely very similar life, like microbiological, like on a micro level, it's probably most likely. But complex life, like animals, yeah, multicellular life, and animals, most probably not. Probably not if we go by these conditions, right? In the 90s, wasn't one meteor or something fossilized bacteria was discovered? I don't know actually. Yeah, I mean they always discover a lot. I mean you just have to go to a museum and they find crazy shit. Yeah. Yeah. So this is the rare Earth hypothesis. There's another factor. Now let's say, what's on evolution? What is there to take? I am a scientist. I believe in evolution, of course. I don't believe in God. What else is there to say? No, they found amino acids in a meteor, which are building blocks of life. Ooh, and they think it came from outer space? Cool. See, I don't know anything about that on a biological level. I think that's super interesting. Now let's say we found all of this, yeah? Let's say we found the habitable time. We found the habitable galaxy. We found the habitable spot in the galaxy. We found the system with a rocky planet in the habitable zone that satisfies all the conditions we went down here, right? Life developed. What now? What now? Well, there's another thing that makes this maybe developing of intelligent life unlikely or mass likely, and this is mass extinction events. Mass extinction. Wait, I can't extinction events. Okay. Amino acids are the steps before life, so I don't count. They don't count as life, but they could provide life basically. Is it possible? Ancient astronaut theorist says yes. You're on when I'm awake? Yeah, Mr. J, I have my science stream today. I do update my science stream on the Discord, guys. You know, so if you read them, they're up every now and then. You know it. Okay. Mass extinction events. Life gets extinct every now and then. We know this. Earth had multiple mass extinction events. Not just the dinosaurs. We had multiple mass extinction events, yeah? Life gets extinct. And that's also we talked about last science stream. So we're not gonna go... Yeah, this is just basically a summary stream of all my science streams. So we're not gonna go in very much detail into everything. Every now and then. But we also learned that it can that doesn't mean bad thing. That does not actually have to be a bad thing, right? It affects evolution, but it can be also a provider and a destroyer, right? Affects double F, right? Yeah. But can be destroyer and provider. I don't know if this is proper English. I just leave it as this. Provider, yeah, there are a lot of species, yeah. You lucked out and came to Malong. Yeah, basically, yeah. So why is that? Because, like, imagine the dinosaurs have not gone extinct. Would we exist? Would we exist if the dinosaurs had not gone extinct? They need a destroyer and provider. Yeah. Oh. We don't know. Maybe not. Maybe the dinosaurs, if they would have not gone extinct, they would have never developed to intelligent life. Maybe they would have never become intelligent. We would have never existed. Right? Maybe we would be hunting dinosaurs and taming them. We don't know though. We cannot know that. We're here because of dinos. Maybe we are only here because they died out. Namely the destroyer of Heralds. That is true. We're gonna talk about that Drake equation. I've seen movies with men and dinosaurs, never turns out well. Yeah, basically. But a fully eradication, we learned this too, is unlikely. After that's unlikely. After microbiological life, is established, right? Is established. Let's just say it. Like, yeah, species go extinct, but there will always be some species that will survive on a microbiological level. So that goes back to say that maybe simple life might be probable, could be more probable than intelligent life, right? So who knows? Who knows? Oh. So other events, or like what events could cause such mass extinctions? Yeah. So what events could cause this? Pictures himself riding Triceratops. Did I pronounce that right? Ark survival shows humans can coexist with dinosaurs? Maybe, yeah. But the thing is, we don't know it. And there's a high chance that we only exist because they got extinct. Simple life, PC and internet. Yeah. Okay, so a change of planet rotation could cause this. Change of planet rotation. It could have a fast effect on how the temperature is distributed on our planet, and some species just maybe do not take it well, right? And then they get extinct. Of course, leaving the habitable zone. That's a no-brainer. Okay, leaving the habitable zone, we get extinct. The star energy output changes. Star energy output changes. An impact of an asteroid, right? Impact event. Too close supernova. Too close supernova. Event. Cosmic rays. Although I mean this, yeah, cosmic rays, gamma rays. And out of curiosity, on your opinion, how did we came up with morality? That is not a philosophical stream. It's a pure science stream. It's about physics, astrophysics. So I don't gonna go there right now. So I wonder if bugs will be the next dominant species. Giant bugs, and then we're gonna fight them. Yeah, I'm up for it. So PC and internet creates TikTok. Is that evolution? That is evolution, yes. Nuclear war? Yeah, I hope we don't have one. Nuclear war? Yeah, okay, nuclear war. Nuclear war. Self-destruction. Wait. Self-destruction. What did I wanted to write here? Oh, climate change. Runaway effect, right? Yeah, we know about that. I like a premise of a couple of sci-fi movies, leaving the Earth because humans destroyed it. Yeah, I mean, we will destroy it. Event change of magnetic polarity. Yeah. That goes with, I guess, leaving the... Yeah, I guess, losing magnetic field, right? Cooling out. Well, although then the planet is basically already dead. Like, this is not... If we at this point, the planet is dead. Although this goes the same for leaving the habitable zone. But okay, we leave it at this. Cockroach can survive nuclear war. So yes, bugs will do it dominant. Alright. Yeah, okay, yeah. Then we have a world of bugs. Maybe they become intelligent, who knows? Maybe, just like the dinosaurs had to die out for us to get created, we have to die out for the super bugs to get created. Mass extinction went another social media platform, yeah. So, okay, let's like conclude this. How long? It's only 1 hour. I will probably, oh god, I'm a bit over time already. Complex life. We just saw that complex life requires, or required, if you go by us, okay, I don't know how to spell that, guys, I'm sorry. Life needs needed very requires. Okay, wait, I will just write it down so I learn it, okay? I will write it down so I learn it. Requires. Okay, actually it's not as complicated. It's not as complicated. Is it wrong of me to welcome us going extinct if we create another Facebook? I don't know, man. I don't want a human. I don't want us to go extinct. Are we for what? Oh fuck! I look at you. Oh my goodness! I can't even. Oh fuck. Okay. Even if you write it, I can't spell it. Fortunate. Fortunate. Interplay. Of events that might not be common. Okay, basically we need to find biomarkers. In other planets. That indicate habitable conditions. To confirm this, right? If we wanna know, like, if we wanna say this is not true, it's actually very common, so what we have to do is find these biomarkers. Self-destruction could also involve biological warfare and creation of AI. That is very true, yeah. Robotic will be the next species to dominate, could be the thing then, yeah. So basically we see why the rare Earth hypothesis could be a thing, right? It requires an enormous amount of conditions to all come together at the same time. If we want to say, okay, that is not true, it's not rare, it's very, very common, what we need to find is start looking for those biomarkers. We start with this, right? We look with this by looking at spectroscopy, sorry, from like other planets. Like if like a planet crosses the sun, okay, let's like see this. Like we have the sun here, like this is the sun. And now we have like a planet crossing before the sun, like right, there's a planet, it goes before the sun. And then it has an atmosphere. Let's say it has like a slight atmosphere, right? Then we can look at the light that goes through the atmosphere because it's in front of the sun. And we can look what light is absorbed by the atmosphere of that exoplanet. And then we can find biomarkers, right? This is, of course, it needs crazy amount of technique. We need to find the planet that we can observe actually with our technology level. And this is what, like, this is the future by looking of biomarkers, right? We have to find planets, we have to need better instruments, and then we can look for biomarkers. Imagine being alive and we find biomarkers on other planets. Oh my goodness, that would be so cool. If that would happen in my lifetime, that would be so fucking awesome. Yeah. So I go back for the people who are new, who just arrived later. talking about this topic, it's very important to keep in mind that we talk about life as we know it. Yeah. We can only make assumption by what we know, because otherwise it's hard to think, right? We don't know what to look for if you don't think about if you think about life that we don't know, because what do we look for even to confirm that is life? But we know our conditions, and then there's life. We believe in other dimensions. Actually, that is. I feel like, yeah, this is complicated again. I should make a separate science stream about this. It's more like I want to believe. I want to believe that there's something really crazy out there that we don't know yet, that we don't have the physics knowledge yet about it, and that would be super awesome. It's more like a want to. I want to believe it. I think that would be super. Pictures Nani in another dimension. In another dimension, I became a Dota 2 professional esport player. Actually, this is Drake equation now. Okay, we move on from this topic, and now this is now different, guys, because the Drake equation, you guys know this, right? Now let's make one thing clear. We are not talking about ships and star citizens. There's no reality where that is possible. Excuse me, Sabitsu. Why? Why do you have to say that? It could be. If there are infinite realities, it could be. Maybe there's another timeline when he believes in another dimension. Yeah, I do. I mean, yeah. Yeah, there's always the question: are we like too stupid to understand the higher dimension, right? Also, I mean, what dimensions are we talking about? That's what I mean. The topic is not it's not straightforward. Yeah, the Flatland. Everyone, if you're interested in that, watch Flatland. It's a really good movie about the shit. So the Drake equation. Basically, when they did it and made the assumption for the equation the first time, they came to a pretty high probability for life to exist, right? For like intelligent life even. And that created the Fermi paradox, right? So what is the Fermi paradox? Talk about this first, and then actually we're gonna calculate today, guys. I have my calculator. And we're gonna calculate today. We actually do calculate stuff with the Drake equation. We're gonna, at the end of the stream, we're gonna have some numbers here. How much aliens exist? How much aliens do exist out there? That's where we're gonna go here today, guys. Fermi paradox? No, you're not. No. Yeah. Very simple math, guys. Very simple math. Don't worry about this. So. The Fermi paradox is the lack of evidence for extragalactic life contradicts the high estimates that exists with the Drake equation, right? Yeah. Yep. Based on its Fermi paradox goes even further because it requires radio. Not only life as we know it, but also life that uses radio. So there are three possibilities. For this to happen. First one, We are actually alone. We're actually alone. Yeah. We're actually alone, guys. Alone, we are unique. Could be, guys. It could fucking be. Alone in the dark. All alone in the dark. Or do they say night? All alone in the night? I think they say alone in the night, yeah. What if aliens have already Twitch and radio? Well, that's what the Fermi paradox talks about, basically. Why don't we see them? If they have that, why don't we see them? Where are they? So yeah, maybe we are alone. It would be so depressing, guys. We are a mistake. We are unique in the mistake. But wouldn't that be so yeah, maybe they're hiding, yeah. Yeah, so actually, yeah, maybe they're hiding. So there are others, yeah, they're hiding. There are other civilizations, right? Civs, but they hide on purpose. They don't want to be found. Like Star Trek, the first directive, don't interfere. Do not interfere with another species until they develop warp technology, right? Out of range, yeah. Like we do when you're about to meet the drunk guy on the street. Yeah. It might be just about time. Yeah. Another possibility is civilizations are actually common. They exist, yeah. But none have managed to colonize the galaxy. Colonize the galaxy. Why? That is another very sad possibility. Another very sad possibility is interstellar travel is impossible. Could be. Could be. Who knows? Yeah, maybe it's about time. Yeah, maybe we don't cross time. Yeah, we come to this at the end. Yeah. Earth is space Australia. No one wants to come here. Yeah, impossible or very difficult. Yeah, or very difficult. Or super difficult. Civilizations destroy themselves. Destroy themselves. Before they reach age of space travel or interstellar travel. Or they don't want to colonize. Like maybe they just don't want to. Maybe they just don't give a fuck. Maybe they just don't give a fuck. They don't give a fuck. Maybe they don't want to colonize. Maybe they're just like, you know what? These stars, they're super boring. Like I don't care. I don't want to know what's up there. I don't want to meet anyone. this. Yeah, they're like you know, they're like people that don't like to go outside to meet people. Yeah. Maybe they just don't like to meet people. Yeah. Yeah, these Earth, that place is fucked. So yeah, that could be. So what we do actually is we do broadcast radio, right? We broadcast radio signal to space since we say about 100 years, okay? This is gonna be easier to calculate later on, so we're gonna say about 100 years. Is it safe to do that? Is it safe to do what? Broadcasting? so aliens find us and then come to destroy us? It's pretty safe actually. We're gonna see this, yeah. Telling the universe we are here. We are here. Why has no one heard us? Why does no one? What? Like, yeah, okay. I don't write it down. Actually, why? If you broadcast into space with radio since like 100 years, why did aliens not hear it? Why is no one answering? Maybe, yeah. Who knows? Maybe they don't want to. Maybe they can't. That is also nuts. It's like standing screaming in the dark jungle. Who knows what could come out here? We were here. Well, in our closed universe, it's... Yes, right. We were here, yeah. But, I mean, depending if we don't destroy ourselves, we might still be there if they hear it, yeah. Although you're right, yeah. City project, yeah. I find it hard to imagine aliens would be hostile. Most problems are caused by competition for resource and aliens would be... Yeah, I think so too, Animo. I'm with you there, Animo. I don't think they're gonna be hostile, no. Okay, so, and we're gonna go about this now. Why? What happens with our radio signals? How far do our radio signals travel, right? How far do they travel? We call it a bubble because it's a bubble. Why is it a bubble? Because it expands spherical symmetrical, right? It's a sphere. Imagine a sphere. It's not linear. The whole Earth is broadcasting. You have to imagine a sphere, right? Sorry, guys. If they're aliens, we would be hostile to them. I don't think we would be hostile at first, no. Yeah. So one problem with radio signals is, well, they do travel with the speed of light. Yeah, light travel. That is true. Which is the letter C. Like speed of light is always marked with the letter C. Like radio waves are not sound waves, right? We're talking about radio waves. For people who are maybe confused about this, for people with a lower background, radio waves are just like electromagnetic waves. It's just because they're not light, they're still waves, they behave like waves. In vacuum, medium is different, but in vacuum they travel with the speed of light. Don't confuse it with sound waves, okay? Maybe they think we are hideous. Yeah, you know, Dr. Wittelsbank, I think, yeah, that could be a big point. Yeah. Yeah, that is true. They would steer, they would steer clear of this planet after watching this. Absolutely. So the problem is, because it travels as a sphere, it becomes more faint with the increasing distance, right? With increasing distance. Eventually it will just blend in with the background noise. Yeah. Background noise. So that means the signal must be strong enough. And just to say why is that the case for the people, like let's say we have Earth here, okay? Like this is Earth. This is Earth. And we're gonna broadcast some. We are broadcasting some radio signals there. As we said, it expands in a bubble. So this is the radius. This you see, like it's not a circle; it's a sphere. Imagine it as a sphere. You think the area on the sphere is now not as big, but if you go far out, let's say you have an increasing distance, right? It's getting even further away. You can see how the area of the sphere becomes larger and larger. The signals have to cover a way larger range, like area, and that's why they become weaker in the end, right? So just need to cover need to cover larger area with the increasing distance, right? Yeah, Goku, we're gonna go to all of this. We're gonna come to this, Goku. You're way ahead of me, Goku. Don't be ahead of me. Stop being ahead of me. Okay. So that means signal needs to be strong enough, right? So signal needs to be strong enough. To reach Earth, but also spoilers, yeah. Spoilers. But also for them to reach us, right? To reach Earth. Wait, no, strong enough to reach us. The other way around, though, aliens need a very big receiver. Need a very big or large radio telescope. And like radio telescopes are expensive, needs to be big. We have some on Earth, right? So are you talking about radio beacons with the sole purpose of contacting other species, radio channels? No, in general, like whatever, broadcasting random stuff or even using it. Like we use it. Like this, for example, just saying to show you the size. We talked a lot about the science stream about ALMA, so I thought I'm gonna show it to you. Like this is from ALMA, right? Oh, ALMA is a radio array, so. Large millimeter and sub-millimeter array. Hey Vash! So large and sub-millimeter. And this is like, it consists of 66 antennas that are 12 meter in diameter, yeah? And this is not made to contact aliens. This is not made for this purpose, right? So you see, you have to cover large areas with these. The largest radio telescope we have with the purpose of contacting aliens is in China. Of course it's in China. Who would have thought something else, right? Wait, I need to push this away. So this is in China, guys. This is like the largest one. It's 500 meter in diameter. X-Files lied to you? So this is 500 meter in diameter, yeah. And this is made for looking for extraterrestrial life, right? It's like the biggest we have. It's called like the eye of the universe or something like this. I don't know actually. It has a name. It's really big. It's really big. Yeah. So and it can reach like 28 light years, right? Reaches. Okay, like diameter. Largest radio telescope. Largest. Telescope. It's in China. It's called fast for like 500 something. It's called fast, something like this. And it reaches like 28 light years. And we're gonna see how this 28 light years fare, but it's roughly about 1,400 stars. That's what they estimate. They estimate like 1,400 stars can be reached with that. That's what she said, yeah. 500 meter aperture spherical telescope. Yes, thank you very much. Yeah. Yeah, that's fast, right? That's shortened to fast. There's one a couple of hours from here, a very large area, so they name it very large. They name it super large, very large. The naming of telescopes is the most funny thing in the world for me, actually. Okay, so remember this. Actually, 1,400 stars is not much. Do you think this is a lot? No, I think this is not a lot at all. I think this is not a lot at all. Yeah. So, 28 light years, yeah. Was it built by China, a group of guys? You have to go to the Wikipedia. I don't know. I just, I have no idea. I think it was only built by China. I don't think, I mean, China does cooperate. They do that though, right? But I don't know actually. You would have to look it up. Okay. The bubble, the radio bubble. Like we are broadcasting since 100 years, yeah? That means would cover, our radio bubble now would cover about, like, would cover a sphere of about 200 light years. Yeah? Why 200? Because in diameter, right? We have to think diameter. We have to think about the bubble. Yeah? It's not just in one direction, it's a bubble. So we cover a range of 200 light years around us. But we learned earlier, it's gonna be faint. The signal is gonna be faint. Whatever they can still, they're gonna need super crazy telescopes, right? This is covering, like this 500 meter diameter radio telescope is covering 28 light years. We are out there to, like, yeah, they won't be able to receive that properly anymore, yeah. Yeah, it's not much, Sabitsu, yeah. It's only like a very small percent of the stars we have in the system, yeah. Absolutely right, yeah. So, the center to our galaxy, the center to our galaxy center. It is like 26,000, something about, yeah, 26,000 light years to our galactic center. Okay, that's the, yeah, we leave the 26,000, thank you. That's, what do 200 light years do? Like, seriously, how much does it even cover? It covers shit, and we are broadcasting since 100 years. It covers the bullshit of our galaxy. Now, just to see, let me see, okay, we are alone in our galaxy, maybe there's life in another galaxy. Radio would not be effective. I mean, Andromeda, our closest galaxy, Andromeda. Okay, Andromeda distance is about, I can't spell, 2.5 million. You may give me the exact number if you want to. So yeah, it's not very good, yeah. We should have broadcasted since the end of the day. Yeah, but as we saw earlier, like, even the signal will be lost by then. The signal will be lost. They won't be able to receive us there. Yeah. Close enough, okay. And just to tell you, like, just because I found it very interesting, the oldest galaxy we have found today, yeah? So the oldest galaxy. And I give you the redshift. 11 redshift, yeah? Redshift 11 for the people who know what I'm talking about. Otherwise, forget it. It's about, like, yeah, billion light years away. Oh, why do I write that down now? I don't need to. And it's like 13 billion years old or something like this. And it looks like this, guys. It looks like this, like, yeah, whatever, I guess. The thing is, guys, let's say species in these old galaxies, a species developed. How are we gonna communicate with them? How are we gonna do that? We need wormholes, yeah. That's an amoeba, yeah. Some numbers I remember, Goku. Some numbers I have to look up before, but like the galactic center I know pretty well. Then there are numbers that are very unsure, like diameter of our galaxy, right? The diameter of galaxy, like, what do they estimate? 100,000 to 200,000? What kind of estimation is that? Like 100,000 to 200,000? That's a large uncertainty. Galaxy only a mother would love, yeah. Yeah, and then the universe is even expanding, another problem, yeah. No, actually, Barker, isn't it the Andromeda collection won't do shit? Because of the cross-section of the stars colliding. Maybe some get collected, but most likely not a lot of stuff will happen because of the cross-section, yeah. yeah, let's just complete it. The diameter of the Milky Way, okay? Just so we have the complete picture. Or we make it here. Milky Way diameter. Let's say the largest. Yeah, let's say the largest. 200,000 light years. Very large. Very large. Other than redshift, is there anyone else that proves that the universe is expanding? Well, I mean, if we stop seeing stars because the light gets dimmer, I guess that will prove it indefinitely. Well, I mean, any kind of waves, right? It's not just like any kind of waves that proves this, right? That the universe is expanding. And it is always a redshift, of course. It's a wave, it's a redshift. So I don't think there's like. No, I mean, yeah, that's about it, I guess, right? I'm just thinking about it. But yeah, all the other waves are still waves. I mean, it's still a redshift. Doesn't matter. It's redshift. Yeah. Yeah, the galaxy Andromeda is blue shifted because it comes towards us. Yeah. Yeah, it's gonna exactly. Yeah, the local gravitational interactions are way much further. It's not gonna happen. Like not much is happening. Yeah, but some stars will probably go into space. Yeah, but the planets will remain with the systems. Yeah. Kind of relieving. Okay. Drake equation? Okay, let's go to the Drake equation. Okay, let's go to the Drake equation, guys. Let's go to the Drake equation. The Drake equation. No, it's not about the Herald, guys. It's not about the Herald. It's not about the Herald. Just that you know. I'm sure everyone here knows the Drake equation. Everyone here knows it, right? If you don't know it, that's fine too, but I get a feeling everyone here will know this better than me. Like 100%. Everyone here will know this better than me. So what does it do? It predicts a number. Of intelligent species. Intelligent species in our galaxy that we could communicate with. Right now. Like right now, yeah. Not awkwardly. You never heard of this? Okay, that is good. I was so afraid I would have a topic that everyone knows already today. Yeah, like I was so afraid that you guys would know that already. It was developed by Frank Drake in 19... Someone give me the number. 1960? Something like that. Okay. So what we calculate, we want to know the number of sieves. So n sieve. Civilizations. Okay. So what can we measure? What can we measure? 61. Thank you very much. 61. What can we measure? Measure? I mean, we talk about measuring, and of course we can measure a lot, but we cannot count the stars in our galaxy, all of them. Like we can count them, but it's like a lot of effort, right? And yeah, there's also a thing of line of sight, right? We cannot really look through the center of the galaxy, so we have to make an estimation. That would be a big fat zero. How many nannies is needed to destroy our hearts in Stanton? Yes. So we could technically, yeah, we could measure the total number of stars in the system. In the galaxy, I mean. In the Milky Way. And we would say this is N Milky Way. We can also measure the fraction of the stars in the Milky Way that have planets. Theoretically, we could that, right? We have the Kepler mission that is going nuts there for the planets, that is finding planets left and right, and yeah. So this is the fraction of N Milky Way. So then it's a fraction of the number of stars that have planets. And we call this FP, right? Then we need another fraction of these planets. We could also measure of these planets the fraction of FP that are Earth-like, like rocky, right? And we call this fraction then Fe. Of this fraction, so we need a fraction of Fe that is in the habitable zone, right? And we call this FHZ. This is what we can theoretically measure. Technically, we can make assumption out of the data we have, right? We have like a certain amount of data and we extrapolate from there. That's how science works, right? So what can't we measure? We cannot measure the fraction of the planets that have developed life. We are not there. We are not there yet. We can't, right? We don't have any kind of sample where we can extrapolate from, right? So the fraction of FHZ that have developed life, which we would say it's FL for life, right? And then the fraction of this with intelligent life, right? With intelligent life. And we call this FE. And then, even if we have intelligent life, right? We had intelligent life on Earth way earlier, but we didn't have radio, so we couldn't communicate with anyone. So fraction of Fi with radio. Technology, of course, yeah. So we say this is FR. And then the lifetime of species. Or the civilization, right? And we just call this T. Alright. That's a lot of letters, and now we're gonna have to do a formula, equation with it, and even if you don't like it, guys, we're gonna do it. It's not bad, guys. It's not bad, okay? You like don't worry about it. Don't worry about it. No, you don't. Actually, no, you don't need it. Well, maybe later. Okay. So this leads to the formula to the Drake equation, the famous Drake equation, right? We just have to put it all together. No. This is alien. No. That's super easy, guys. It's super easy. Look. We take all these fractions and we talk about this. Don't worry about it. Wait. NFP when FHZ FL FE FR and T. Drake equation. Okay, guys, we're gonna write it down here again, just so you know what we're talking about. Okay, what did we have? We had NMV times fraction of the planets, fraction of Earth-like planets, fraction of Earth-like planets in habitable zone, times fraction of planets with life, times fraction of planets with intelligent life, times fraction of planets with intelligent life in radio, times time. Now we have to talk about the time, because this is a number. We want to have a number, guys, right? At this time, because we have time, we still have a unit, so we have to eliminate the unit here, right? What we mean with this is basically the time span. Oh wait, time span of the species. When counting sieves, do we also count call to power, MASE, or just the main 6? What? What? Okay, guys, this is the time span. Of a species. No, why do I say species suddenly? I'm always saying sieves, transmitting radio. Yeah, but the problem is we need to normalize it, because we only want the number, we don't know, so we need to normalize it, and that's why we have to divide it by the average time span of the Milky Way. Yeah, normalize it. So we need what T actually is T is lifetime of sieve divided by the average lifetime of the Milky Way. Yeah, or we take the average lifetime. We don't actually know. We could otherwise, if you don't do this. Oh, the game series Civilization. Okay. Evolved what? What do you mean evolved? So if you don't do this, you need to use here, you need the star formation rate instead of the number of the Milky Ways. Stars in the Milky Way, you just need the number, but this is fine, guys. So we just divide this, right? The average lifetime of the Milky Way is about 10 gigayears. I think we say 10. We say 10 gigayears. I think. Sorry, guys. We come to this later, I guess. So let's talk about the values. Let's talk about these values. This here. Wait. We make a minimum estimation. So like we make a negative one. That's what you always do with the Drake equation. You take a pessimistic one and you take an optimistic one, and you're gonna help me get these values after we come to the first ones. Yeah. Eat had a sec. Alright, Broderick, good night. Have a good night. And thanks for attending. Makes me happy when people attend this. Okay, so we're gonna make an optimistic one and like a pessimistic one. So normally you say it's like 100 billion years to 400 billion stars, not years, billion stars. So our pessimistic estimation would be 100 billion, and our optimistic estimation would be 400 billion stars. I haven't looked too deep into this. This is just a general value. You assume often it could be more, could be less, right? Now the number of planets, and this is where you start estimating. And just for you to understand, right? Let's say you take like the in value of 0.1. This means 1 out of 10 stars have planets. And 1 means all stars have planets. Now, the thing is, this probably most likely goes as 1. We have the Kepler mission, and in general, most stars have probably planets. Like, we find a lot, and our like technology gets even better. Sometimes we cannot find them because our technology is not there yet. It's very hard to find them, right? So we say the very optimistic one is definitely we're gonna take 1 for this, for the optimistic one, and then we're gonna take a pessimistic one where, I don't know, we take a lower value. You can decide, guys. You can decide, all right? You have to think with me here. We're gonna work together. Now for FE and FZ, we're gonna take this together, right? We're gonna take this value together. This is basically habitable, right? Habitable. Well, I mean, nowadays stars have iron. Yeah, the newer stars nowadays because of the supernovas. Yeah. That's the thing. So okay, the Kepler mission, and I looked this up. I looked in a paper, and basically they took part of the they took part of the planets of the Kepler mission, and then calculated how many have Earth-like planets, and they came to the conclusion that it was like 22% of the sample of planets are like Earth-like, habitable, basically. And we have to assume it's hard to detect, okay? Hard to detect. Like if aliens would look at our systems, like let's say aliens would look at our systems, what would they find? Maybe they would see only 1 planet or only 2 planets. Maybe they would see Jupiter or whatever, but they wouldn't detect Earth, right? So we're gonna have pessimistic here too, and we're just gonna go with like 0.2 for the pessimistic one, and we're gonna go with 0.5 then for optimistic one, right? We have to see about this. But it is basically very hard to detect. FL. Now, what value do you want to have for FL? It's the same. If we choose the value 1, we say every planet detects every planet that is habitable develops life. Do we think that? I didn't cancel it. I wrote it, Pex. If you saw on Discord, I wrote clearly. I wrote that. I just have to. Are you misread? Oh, I'm so sorry, Pex. Yeah, I'm sorry. Anyway, so guys, what do you think? Do you think that if a planet is habitable with our conditions, will it definitely develop life or not? Okay, Bergman, have a good night and thank you so much for being here. Yeah, I'm so sorry this is such a late science stream, but I didn't want to cancel it. I wanted to do it, so I made it late. Anyway, so we could go with a positive, like, if you take 1, that means every habitable planet develops life. If you take lower, then that means less. I guess we're making a lower estimate also. Like we could always like I I don't know. I don't know what would be reasonable here, guys. I don't know. We're gonna take a lower one. And then intelligent life the same, right? Intelligent life the same. I would take a very low one for this. I have to say. I mean, intelligent life maybe 1 out of, I don't know, 10,000? 1,000? Let's say 1,000 is like a very good estimate, actually. Most likely. And the species that develops radio. Now here I'd say, if we have an intelligent intelligent species, I would say that it's most likely that they're gonna develop radio. I think this is probably most likely, yeah. So I would say, yeah, if they're intelligent, they will most likely develop radio, yeah. All intelligentive develop radio. Now the lifespan. Okay, we say Milky Way lifespan. 10 gigayears. Now our lifespan. We are broadcasting, we saw this earlier, we are broadcasting radio since 100 years. So I would say, what is a low estimate? How long are we still going to broadcast radio, guys? 200 years? Let's say the pessimistic one is 200 years, and the optimistic one is like 1,000 years? 1,000 years? Internet killed the radio star? Yeah, I don't know. Let's go with this. Okay, let's go with this. Okay. Okay, guys. Let's calculate. And pessimistic. And pessimistic. 100 times what we say planets. Pessimistic, let's say, like, actually, yeah, let's say out of I would say, I don't know, guys, I would actually say this is pretty high, but so let's say the pessimistic one, let's say 5 out of 10 stars have planets. Okay, let's say this. Okay, the habitable planets. Now we take the pessimistic one, we take the 0.2, right, from what they estimated from the Kepler missions. Now, developing life, will every habitable develop life? Let's go be pessimistic about this and say I don't know, guys. What do you think? How many planets will develop actually life if it's actually habitable? I think it's mostly likely. Let's say 0.1 actually. Let's say pessimistic. Out of 10 planets that are habitable, 1 will develop life. Now intelligent life, pessimistic. I don't know. Let's be very pessimistic about this. Let's say 1 out of 10. No. 1 out of 10,000 planets will develop life, okay? Intelligent life, I mean. Radio? Okay, let's be pessimistic about this too. And like say 1 out of 10 intelligent species will develop radio. Now the lifespan, we know this is 10 gigayears. So 10 to the power of 11, and our lifespan, yeah, I don't know. I mean, guys, 200 years, is that a low estimate? Is that a low estimate? Look, should we just go with 100 years? When we say we did radio and say 100 years, okay? You can calculate it if you want to. I calculated later. If you want, you can already calculate it. Optimistic. Now 400. Like optimistic one is every fucking star has a planet, right? Everyone has a planet. And for here we take like, okay, 0.5. Every planet, habitable planet develops life. We get an optimistic one, yes. And we like here we take like 1 out of 1000 develops intelligent life. And they will definitely develop radio. And we're gonna broadcast for 1000 years, okay? Let's be pessimistic. Let's be pessimistic first, okay? And pessimistic. And optimistic. No more radio. Yeah, no more radio, guys. No more radio. So 100. Oh, I can't actually see anything. It's too dark. And then we go like 100. Oh my goodness. That's super low, isn't it? I can't read that. My calculator is broken, guys. My calculator is broken. I can't fucking read that number. It's too dark. Okay, wait. I have to go into the light. Okay, wait, that is very low. I can't calculate it on the PC, yeah, I'm stupid. Okay, to minus 14. That is super low though, right? Is it not? No. Maybe we need to estimate the longer time span of us. Yeah, I think the time span fucks us, guys. The time span fucks us. -9. Oh, it's 100 billion years. So, sorry, yes. Okay, wait, yeah, I can't, oh my god, I forgot about this. Why did I just write 100? Okay. Yeah, guys, I'm stupid. Sorry, guys. I'm so sorry. This is, of course, we're talking about billion. We're talking about billions. So this is like 10 to the 11, and this is like 4 times 10 to the 11. I'm so sorry, guys. Okay, yeah. Okay. I'm sorry, guys. It's late. It's late for me, okay? It's late. Okay, so I get like 2.85 to 10 times -5 for this one. That's not too bad. Not too bad. Is that correct? Someone can confirm my calculation, or did I make a mistake again? Okay, I realize this light is not good if I want to calculate something. I can't reach it. But Sabitsu's right. I am on a PC. Could just calculate it on a PC. 2. Yeah, okay, that's the right dimensions. 2. Okay. By optimistic assumptions, guys, there are 2 civilizations. 2 that we can communicate with right now, technically. Like, we would be able to communicate with if we could reach each other in a proper, like, if radio would actually reach us, yeah. What did you miss? A lot. We actually covered a lot today. I'm already going overtime today. This is way too long, actually, already. My brain stops working. Is that a lot? Is that a lot, guys? No, it's not. It's actually not. That are very optimistic assumptions. I don't know, guys. Maybe the rare Earth hypothesis is right. Maybe the rare Earth hypothesis is right. I don't know. Maybe we don't have to worry about the Fermi paradox. We just don't have to worry about it. I mean, with pessimistic assumptions, we don't even like whatever, right? But with optimistic assumptions? Now, let's say we increase the lifetime. That will make the biggest impact. I'm also done with one info civilization, yeah. I would say the biggest impact here is like the lifetime, right? Multiply that with frequency, bring the math properly. I think it's like baking cake. Any plate made the same material at the same temperature will create similar results. Right, but then is the question, Animo, how many planets are there with the same conditions? Big question, right? So I want to conclude this here now. My brain stops working. It's late. I'm overtime. Okay, so one big condition. Someone said it earlier, right at the beginning of this. No, in the middle of the stream. There's another big condition. The life of civilizations have to meet up. Right? So, let's say this here. So let's say this is time. Oh. This is now. This are we now, okay? This are we now. And let's say like we are this. We are this. We are like in here, but we existed a long time and now we have radio, right? And maybe another species developed before us, like they were here. And then, well, I don't know, they got destroyed, wiped out, they stopped existing, whatever. Assume we don't live infinite. And maybe after we destroy ourselves, there's gonna be another species, maybe like here. And then, how are we gonna communicate? How are we gonna meet up? This is another very important condition we have to see. And then we have to think about another fact, guys. The biggest star formation in our galaxy has already happened. Every galaxy has a peak. We have already been there. The star formation rate is declining. Midlife crisis, yeah. Exactly. Yeah. Star formation rate is declining. Or not the rate, like in general, yeah? Habitable zones are getting smaller. We learned that. So if you increase the time, you may have solutions to the Fermi paradox that can sphere broadcast radio at stellar distances. Yeah, that's the question. Yeah. What can that? Yeah. Stars himself, which has will devote that much energy to broadcasting radio as opposite to going and using star for, I don't know, funding the education department or something. Yeah, absolutely. Yeah, you have to think about this. Yeah. It's okay. Yeah, okay. That could be a Fermi paradox solution, yeah. Well, 2000 light years. The question is, can we even detect it in 2000 light years, right? Can we even? So, our galaxy has already been as a peak, yeah? Every galaxy has a peak. And we already had ours. So there are probably most likely not a lot of planets, stars being still developed that can host new civilizations. Maybe we'll never have a chance. Because that's it for our galaxy. Nothing more is coming. That's basically it. We have to think about that. Okay. That was a long science stream. That was a very long science stream, guys. We learned, oh, god damn it, we learned quite a lot. Where did we start? This is where we start. We started with the rare earth hypothesis. We recapped basically the other science stream. Maybe we understood, maybe, we don't know, yeah. Yeah, we were saying this here. Like, we have a radio telescope right now. The biggest in China. Reaches 28 light years. 28 light years. 1,400 stars. That's not a lot. That's not a lot. And it has to be 500 diameter. It's 500. It's gigantic. Look at the technology stuff we have to build for to even reach this, right? So yeah, we recapped all the stuff in the other science team with the rare earth hypothesis. Why maybe we are unique and special. Maybe why we haven't found other civilizations, like maybe we are unique or they don't want to be found, or interstellar travel is impossible, stuff like this, right? We looked at the radio transmission we have nowadays and what we can. Unique, maybe special, no, yeah, alright, unique. And we looked at the Drake equation and we came to the number, for an optimistic number, we came to the conclusion that right now we can maybe communicate with 2 other civilizations. But this only assumes, like, yeah, go do it yourself, guys. Think about the number, think what would be possible, and like see what you can result in this, right? And yeah, we have to meet up as well. You very much enjoyed this. Yeah, I hope you enjoyed it, guys. I had a lot of fun as always. I really like doing these. And so I hope you enjoyed it too. I really do. So thank you very much, Dr. Wiggisbang. Yeah, because now this is the end. This is the end now. Yeah, I apologize for having it so late, but family comes first. That's always how it is, right? I hope you learned something. I learned something for sure, and I hope you too. I will try to make the next science stream within a month. I don't know the topic yet. I don't know if I maybe redo the first one because I lost it. I really have to think about it, but I will try to do the next one in a month. And if thank you so much. Thank you so much, Rockstar. Crazy. 1,500 bits. God damn it. Yeah. we change maybe the topic, and I still have to think about what topic we go next. It will be astrophysics, yeah. Drag equation, not this kind of drag equation, not this kind of drag equation, this kind of drag equation. That's how we work. So yeah, guys, thank you so much for being here. I will go to continue with stream gaming the next week, and hopefully do the next science stream in 1 month. Yeah. Black holes are always time for. Yeah, I want to do a topic about black holes. Absolutely, I want to, but I have to see. Yeah. Made my evening, finished broadcasting some data for the astronomy project I'm helping. I was looking over Hayden Age and noticed your stream. Ah, that is so cool. Ah, you actually have to do. Ah, God, back awful. That is so cool that you can do that. Hey, glitch, reached the end. Yeah. So yeah, tomorrow back to gaming, guys, and I will notify you on the next science stream. Either my Discord, and actually I do notify on Twitter about that, but I forgot today because it was a crazy day. What can I say? What can I say? Any case, if not, I will update this command. You can come here and in my chat when I stream, you go in science, and this is no from today, but I will update, if I have the new date, I will update this command, and then you see when the next science stream is. I will upload it also on YouTube for the people who want to rewatch it in double speed because it's so slow. And yeah, guys, thank you again so much for being here, and thank you, Roxa, again. And I hope you had fun. I very much had some fun. So guys, have a great evening or morning already, or day, wherever you are in this world, and see you in the future. Yes, live long and prosper, guys, and see you in the future. Bye bye. Bye bye. And